From the heartland of America and the gateway to the West, good morning, good evening, wherever you may be across the nation, around the world. I'm George Norrie. This is Coast to Coast AM. Later tonight, protecting the power grid. We will not stop until we protect that grid. Here's what's happening. Nuclear war is the inevitable conclusion of Russia's invasion of Ukraine, according to a Russian general who wrote that nation's war Bible. The chilling forecast came from retired Major General Alexander Vladimir, who penned Russia's 3-volume book called The General Theory of War. Dr. John Curtis, onlinecolumnist.com, with us is here. John, you've been warning for months now that this war's got to settle, but what about these possibilities of nukes?
Well, I don't think there's any question about it. Even Biden said, or if he remembers what he said about a year ago when he started talking about how the U.S. was going to commit troops to Taiwan and start another front with communist China. He said that we're closer to Armageddon. Do you remember Biden saying that?
Yep.
Well, the Association of Atomic Scientists has said that the clock is closer than it's ever been to a nuclear holocaust, okay? And they're not known for their hysteric predictions. And this general, who's written the book on it, basically said that survival and continuity of the civilization is all that counts to Putin and all that counts in any war. And a war of annihilation could very easily start. And once it does, George, it's going to be very hard to put it out, because once the button is pushed on one of those ICBMs and it happens to flatten and kill 10 million people in New York City alone as a first strike, I mean, you're talking, there's no mutual assured destruction here. What is the U.S. going to hit in Russia? The Kremlin? Moscow? I mean, that's a very impoverished country over there. We've got a lot to lose here in the United States. And when you look at the fact that this is the first president in U.S. history, post-World War II history, we're going back almost 80 years, who has not worked on nuclear non-proliferation after the bomb was dropped by Truman twice. This president has totally ignored that responsibility that he has to engage in arms control and diplomacy and the hard-fought détente that the John Kennedys and Lyndon Johnsons and Richard Nixon and Gerald Ford and Jimmy Carter and Clinton brought to this country. This president has brought us a proxy war with Russia, claiming that the reason why we're in this war is because Putin is going to take over Europe. That is the most preposterous explanation imaginable. NATO is there to protect Europe. Putin has not attacked a NATO country. What he did was obviously barbaric and wrong. But that doesn't mean that cooler heads should not prevail in this and end this. And I liked what I heard from Ramaswamy today. He said Zelensky is outrageous, demanding more cash to hold an election that has been postponed because of this war, asking for more money from the U.S. when he's received over $125 billion. So, yes, we are in the most dangerous place, George, that we've been in our lifetimes, far worse than anything in the Cuban Missile Crisis. And somebody has got to be able to prevail clear heads on this.
Well, it's got to be sooner than later, John. Thank you. John Curtis's website, onlinecolumnist.com. The investment bank Goldman Sachs now sees a 15% chance that the U.S. will slide into recession, but that's down from 20% previously, as cooling inflation and a still resilient labor market suggests the Federal Reserve may not need to raise interest rates any further. That's good news. Bank of America is shutting down several locations in California, branches in San Marcos, Los Angeles, and Anaheim. They'll still have banks, of course, but they're closing some. They were joined by Wells Fargo and J.P. Morgan as they were shuttering branches, too. So far, more than 1,100 bank branches have shuttered this year from all kinds of banks. Charles Koppis, investment advisor, author of America's Financial Reckoning Day. Is it the internet that's doing it to these banks, Charles?
Yeah, pretty much. This is a trend we've seen since 2008 with Wells Fargo and J.P. Morgan and some of the big banks. 1,100 closings this year. We had 3,000 closings in 2022 out of 78,000 branches in the U.S. But some of the reasons are obvious. During the COVID years, there was about a 35% increase in online banking, and the banks are shifting to this and a more digital focus as they face competition with financial tech companies, payment apps, smartphones. 25% of their customers use computers for banking, like I do. And heck, today you can even get a loan online, Rocket Mortgage or something. But another factor, I think, is regulatory compliance costs have really increased for the banking sector, just like healthcare everywhere. And about a third of these branches are in low-income communities, I guess, in that area as well. In fact, L.A. had several close last month as well. But, in the era of low interest rates, it's really hurt bank profits, and we've seen a lot of bank mergers in the past few years, and this just leads to more branches being closed as well, like J.P. Morgan did this year when they took over Republic. But now the Fed's raising rates, and we're having a negative effect on the banking sector, and low-yielding bond portfolios and losses that they've had. This has already led to bank failures earlier this year we've talked about. We've seen several banks getting downgraded even more, and this is likely to get worse with commercial real estate losses. We've yet to see that. And, of course, more people are moving into cash and money market funds and so on. But some are promoting or predicting the idea there'll be no bank branches by 2034, as the sector moves to a more digital platforms and a cashless society. But I think we're already seeing that with the central bank digital currencies right now. Again, during the COVID years, a lot of people started using cryptocurrencies, and the banks are trying to maintain a monopoly here and regulate cryptos and so on. In fact, Jim Rickards calls CBDC Bitcoin's evil cousin, and I just put that in my last newsletter because it would force you to use their legal tender. It would be a complete loss of privacy. They would force negative rates, carbon social credits, back certificate, taxes and fines. They would even control the velocity of money with tokens that might expire and so on. So it's a very bad idea. And at the pace these bank mergers are going right now, we could just end up with 5 or 6 too big to fail banks in the U.S. and maybe the world. I don't know. And it would, be a lot easier to adopt central bank digital banking system and so on. I guess that's why I like the privacy of gold and silver, because it has legal tender status in many states now, 12 or 15. And, as far as the future for banking in this digital age, I think it all depends on the reliable power grid and infrastructure, and that would be really something if we had an EMP attack, and perhaps that's something your guest will talk about tonight, George.
Later on. Thank you, Charles. Always good to talk to you. An exoplanet is a planet found outside of our solar system, and many have already been discovered. In a moment, astrophysicist Joshua Winn joins us. His work is called The Little Book of Exoplanets. We're going to talk about some space next on Coast to Coast AM. And welcome back to Coast. George Norrie with you. Josh Winn is a professor of astrophysics at Princeton University. His research group explores the properties of planets around other stars and tries to understand how planets form and evolve and make progress on the age-old question of whether there are planets capable of supporting life out there. His latest book is called The Little Book of Exoplanets. Josh, it's a great book, by the way. Welcome to the program.
Thank you very much, and I've been looking forward to this conversation.
These exoplanets, how many have been discovered so far?
Well, NASA maintains the closest thing we have to an official list of exoplanets, and I checked just before the program, and the official number is 5,502.
That's amazing.
It is, yes. It's one of the most rapidly advancing fields of astrophysics.
Considering 30 years ago, we didn't know of any of them, right?
That's right, yes. It's a new field. It's very much technology-driven. And it was only in the mid-1990s when technology advanced to the point that we could start discovering planets around distant stars, well outside the solar system.
What percent would you guess that a star, wherever it may be, would support planets?
Yeah, that's a good question. So there are too many stars for us to search them all, right? There's maybe 100 billion stars in the Milky Way. So what we do is we search the nearest, brightest stars. Those are the ones where it's easiest to find planets, and we do a kind of a census. And based on what we've seen so far, it seems likely that, at least for sun-like stars, most or all of them have some kind of planets. To be a little more specific, if you pick a random sun-like star, there's at least a 30% chance that it has one of the types of planets that we can detect today. And we can't detect all kinds of planets. Some planets are much harder to find than others. Planets that are very small are difficult for us to find. Planets that are in very wide orbits are difficult for us to find. So there's like a 1 in 3 chance that it will have a detectable kind of planet, and that leaves plenty of room for the others that probably have the types of planets we're only just beginning to be able to detect.
And Josh, of those planets that might be out there, what percent do you think might be Earth-like?
Well, it kind of depends on what you mean by Earth-like. The one thing you need to know about exoplanet science is that we can only learn a very limited amount of information about each planet. So if we have a planet in the solar system like Mars, I can show you beautiful images of the surface of Mars, and you can see mountains and valleys, and you can look for water at the ice caps and so forth. For exoplanets, they're so hard to detect that we have none of that kind of detailed information. Most of the time, all we know is the size of the planet, the overall size, the mass, and we know how far away it is from the star that it's orbiting. We know how fast it's moving in its orbit, and we might be able to measure the shape of its orbit. That's about it. So when you say Earth-like planet, many of your listeners are probably thinking about a planet that has continents and oceans, maybe breathable air, that sort of thing.
Right.
We have no way at the moment of knowing whether those things are true for any exoplanet. But if we just ask, okay, well, what about planets that are the same size as the Earth and that orbit a star like the Sun and are about the right distance from the star to have the same surface temperature as the Earth? That's kind of a working definition of Earth-like based on things that we can measure today. And the answer is that they're probably not. We actually struggle to detect such planets. That's kind of right on the limit of our technology right now, to detect planets as small as the Earth.
Right.
But it seems to be that maybe 10, 20% of sun-like stars have such a planet.
Josh, how does a planet even form?
That's a great question, and that is one of the big questions that motivates this field. Planets and stars, they didn't just pop into existence with the Big Bang. They had to form. The early universe, was just a kind of formless sea of atoms. And somehow or another, some process must have created the sun and the planets and other stars and their planets. And the current theory is that this happens mainly due to gravity. When we look around the galaxy, we see lots of clouds of material, mostly hydrogen gas, but all kinds of other stuff is mixed in there too. Mm-hmm. And every now and then, one of those gigantic clouds of gas starts contracting under its own gravity. Gravity, as you know, is an attractive force. Everything attracts everything else with the force of gravity.
And it's universal, right?
And it's universal, yeah, as far as we can see. And so that will cause the cloud to start shrinking under its own gravity. And what happens is that if it contracts strongly enough and gets to be small enough and dense enough, then the material can ignite and become a star. It can start nuclear fusion reactions that give stars their power sources. But it doesn't just all collapse into a point like a star. Instead, what happens is the material ends up swirling around this newborn star like a vortex. And that spinning pattern of material, that disk of material that surrounds a young star, that is supposed to be where the planets formed. The planets kind of congeal out of this material that swirls around a newborn star for several million years. So that is the kind of essence of the modern theory of planet formation. You form a star by contracting a giant cloud of gas under its own gravity, and then the material that doesn't quite make it down all the way to the star swirls around for a long time, millions of years in fact, and that gives enough time for small objects within that spinning disk to conglomerate and join together and get larger and larger and become planets.
And in our solar system, Josh, the one planet that didn't get its act together and form is probably what they call the asteroid belt now, right?
Yeah, that's right. So there are actually two places in the solar system where we see a lot of small debris, asteroids and other objects of similar size. One of them is between Mars and Jupiter. That's the asteroid belt that you just referred to. Probably what happened there is we're looking at the material that would have come together under its own gravity to become a planet, but Jupiter is right next door. And Jupiter is a very massive planet, and that means that its gravity stirs up the material in the asteroid belt and probably prevented it from forming a full-fledged planet. The other region that's like that is out beyond Neptune. There's another zone where we find lots of small rocky and icy bodies, and that's called the Kuiper Belt.
That's right.
Probably what happened there is that material might have become a planet eventually too, but everything happens so slowly out there. The further you are from the sun, the weaker the sun's gravity, and the slower all of the motions are out there. Mm-hmm. And so they couldn't get it together quickly enough to form a planet.
Josh, you mentioned the Big Bang. And I got to tell you, I have interviewed so many scientists on this program over the years. I still don't understand the Big Bang, how something would start from nothing. Have you come up with your own thoughts about that?
Yeah, so I don't know why something started from nothing. I think that's one of the large kind of imponderable questions that we have today. But I do know the evidence for the Big Bang, the fact that we have pretty good reason to think that the universe is expanding. That is, when we look at distant galaxies, we see that the distances between galaxies are growing with time. And that means that if we trace back the clock about 13.7 billion years, I think is the current estimate for the age of the universe, that the universe was in an extremely dense state, that all of the matter that we see and spread all over in distant galaxies was actually quite close to each other. So it was a very hot, dense sea, as I called it before, of atoms. There's actually a lot of very solid evidence for that. And the evidence can take us all the way back to the first few seconds after the Big Bang. We understand, we think, the conditions at that moment in the early universe's history. And the reason is that when we look around the universe, we see it's mostly hydrogen, but there's also some helium. Hydrogen and helium are the simplest kind of atoms that there are. And so there's 3/4 of the universe is hydrogen, and the other quarter is mostly helium. And the only way to make sense of that is to suppose that these elements formed in that early hot, dense phase of the universe. And if you calculate, well, what would be the elements that formed from a hot, expanding fireball with the conditions that we think existed in the early universe, you get the right answer. You get that, well, there should be about 3/4 hydrogen, and most of the rest is helium with a little bit of lithium and so forth. So the evidence can take us back to the first few seconds. But then if you ask me, well, what about beforehand? That's where we have to go off of the path of the evidence and start speculation.
Let's talk about some of that speculation when we come right back. Joshua Winn with us. His book is called The Little Book of Exoplanets. His website is tied into Princeton University, and we've got that linked up as well at coasttocoastam.com. By the way, that's Jackson Browne who sang that great bumper song. It's one of my son's favorites. His name's Jonathan, but that was Jackson Browne who sang that song. We're back with Joshua Winn. And Josh, we were just speculating on the beginning of everything. I mean, if you had to write a paper on just how everything started from nothing, how would you start it?
Yeah, that's a good question. It's kind of...
And let's take God out of the equation for a moment, if we can.
Sure, yeah. I like to... I mean, one of the things that you have to do when you're a scientist is you have to tolerate ambiguity. You have to tolerate ignorance for long periods of time. We just don't have a physical theory that can carry us to before the Big Bang or to the very earliest moments, before the first few seconds, like we were discussing a while ago. My colleagues over in the physics department, they have plenty of ideas about what might have happened and whether the universe is a quantum fluctuation and whether there are multiple universes and so on and so forth. I'm much more of an empiricist. I like to follow the evidence, and I like to find new evidence. And it might just be a long time before we have any evidence that will give us clues about what happened at those very earliest moments in the universe.
And, I'm thinking chronologically that things must have beginnings and ends. Maybe that's not the way to start.
Yeah, I do have a colleague over in physics. His name is Paul Steinhardt, and he thinks, where he has published papers about how the universe might be cyclical. That is, it doesn't have a sharp beginning and a sharp ending, but constantly goes through periods of expansion and periods of contraction and periods of expansion again. And there's some underlying physics behind it that I don't quite understand, to be honest with you. But it gives you a sense of how little we know, that we don't even know whether the universe truly had a beginning or whether there are multiple universes or cyclic universes.
It's one of the greatest puzzlements out there, I think.
For sure.
It really is. Tell us the need for exoplanets. Why must we study them?
Oh, good question. So it's not a very practical field. Astronomy in general is no longer such a practical field. It's not going to help us solve any kind of pressing problems we have here. But it does satisfy a really deep, basic curiosity we have. I know a lot of people tune into this show because they like exploring. They like exploring topics, ideas that are sometimes far from the scientific mainstream, or that they like exploring, and that's what we're doing here. Astronomy is kind of the ultimate exploration. There really are other worlds out there. We learn about the planets of the solar system in elementary school, and there really are countless other worlds out there waiting to be discovered. And how can we resist? If we have the technology to do it, why wouldn't we?
Speaking of technology, Josh, what kind of technology is allowing us to find these exoplanets?
Yeah, excellent question. So it's very hard to detect exoplanets. And the basic reason is that planets, although we think of them as huge, the Earth is this huge thing, they're actually much smaller than stars. The Earth is 100 times smaller than the Sun. And also, planets don't emit much light of their own. They reflect a little tiny portion of the starlight of the star that they're orbiting, but they don't emit much light of their own. So, let's say you're an alien astronomer and you're 10 light years away, and you're looking in your night sky and you see the sun in the sky. How could you detect the planets of the solar system? Could you detect the Earth? How would you do it? Well, one thing you might do is get yourself a telescope, take a picture of the sun, and then search the picture to see if you can see any planets going around it. But in practice, that's almost impossible, because when you make the picture, all you see is this enormous bright glare from the star at the center, and any planets going around it are totally lost in the glare. It's like trying to find a firefly when somebody's shining a searchlight right in your eyes. So that method doesn't work very well. It has worked in a few cases, the so-called direct imaging method, but most of the time we use sneakier methods. And my favorite method is based on eclipses. That is, every now and then, if you're looking at some distant star and it has a planet going around it, if you're lucky, the planet will go right in front of the star.
Uh-huh.
It'll cross right in front of it. Now, we can't see that, right? It's too far away to actually see the little tiny planet move across the face of the star. But we can tell it's happening because the star appears to get slightly fainter.
Uh-huh. And then comes back again.
That's right. It's a miniature eclipse. And we've gotten very good at making precise measurements of the brightness of stars and tracking it over time. So remember I said before that there's something like 5,500 known exoplanets. About 4,000 of those were discovered through this method I just described, based on eclipses, or the technical term is transits. We say the planet transits across the star.
Are there some planets, Josh, that move quicker than others around their stars?
Yeah. So what determines the speed of a planet is how far away it is from the star. The closer you are to the star, the faster your orbit, and the less time it takes to go all the way around. So, for example, in the solar system, Mercury is the closest planet to the sun. It goes around every 88 days. And if you get way out to, say, Jupiter, which is farther away from the sun than the Earth, that takes 12 years to go around.
Wow. That's a long year.
Yeah, and there's a lot of variation. You know, we found planets that are very close to their stars, and we found planets that are extremely far away, and everything in between. In fact, it's kind of amazing. There are some planets. So I said Mercury goes around the sun every 88 days, and we consider Mercury to be close to the sun. It's an inner planet of the solar system. But around other stars, we have found planets that only take, say, a few days to go all the way around their orbit.
A few days? Wow.
They're tiny little orbits that are just hugging the stars that are next door. They're almost as close to the star as it is physically possible to be without being destroyed. Those are some of the most surprising discoveries we've had so far.
I bet it's hot on that planet.
Yeah. Yes. So one of the types of planets like that they're called hot Jupiters. They're just as big and massive as a giant planet like Jupiter is, but instead of being way out far away from the star, they're extremely close in, and so they're heated to thousands of degrees. In fact, that was the first really major surprise in this field. In 1995, one of the very first discovered exoplanets was a hot Jupiter. And we don't have anything like that in the solar system. And in fact, we had a theory, the theory of planet formation that we were describing earlier, that seemed to rule out the existence of such planets. In this theory, the only way to become a giant planet is to form far away from a star, because there's a lot more solid material out there that's available to form a planet. You have things like water and other molecules are frozen if you get far away from the star, and that adds to the inventory of solid material. But if you're really close to a star, it's so hot that all of the solid material vaporizes. So you shouldn't be able to form a planet so close to a star, let alone a giant planet. And yet one of the very first discovered exoplanets was a hot Jupiter, where nobody would have expected it.
Right. And let me ask you this, Josh. Let's assume there is intelligent extraterrestrial life out there. With high technology, they've had, let's say, millions of years advance over us. would they have been able to have spot Earth from their planet outside the solar system and determine the possibilities of life here?
So I don't know about how technology will develop over millennia or millions of years. That's beyond my imagination right now. But I can tell you this: if they have the same technology that we do, and they are located, like I said before, 10 light years away, they would have no problem detecting Jupiter. Jupiter's the easiest planet to detect because it's so massive, and it causes the biggest effects on the planetary system. They would struggle, though, to detect any of the other planets. They might be able to detect Venus. Mercury's too small.
But that's with our technology.
That's with our technology. So that's where we are right now. We're pretty good at detecting giant planets, and we struggle to detect planets as small as the Earth and Venus and Mars and Mercury. Now, give us another few millennia of technological developments, and even though I can't predict, what the technology will be, it seems very likely that they would be able to detect all of the planets in the solar system. If we've only been doing this for a few decades and we've gotten as far as we can,
right,
it won't take that much longer before we will have much more complete knowledge of exoplanetary systems.
Josh, what is the NASA TESS program?
Yeah, so TESS is a NASA mission. It's an ongoing NASA mission, and it tries to find planets using this transit method. TESS is an acronym. It stands for Transiting Exoplanet Survey Satellite. So it scans the sky looking for exoplanets. The way it works is it's a spacecraft that has 4 small telescopes on it. And each small telescope is pointing in a slightly different direction. And so together, they can monitor a big patch of the sky, about, say, 1/30 of the entire sky at once. And so for long periods of time, all that the spacecraft is doing, it's automated, is making images over and over again of that part of the sky. And then we use that data to measure the brightness of all the stars in the image. Maybe it's 50,000 stars at a time, looking for those rare events when the star gets fainter, usually for a few hours, because a planet goes in front of it. And so that's one of our main engines of discovery right now, is the TESS spacecraft. It was launched in 2018 by a SpaceX rocket, in fact, and it's in an interesting orbit around the Earth. It's in a elliptical orbit. So it's on one end of the orbit, it gets close to the Earth, and that's when we can send all the data back to the ground and analyze it. And at the other end of its orbit, I think it's about 2/3 of the way to the moon. So it really goes far out there. And that's because it's really useful for a space telescope to be far from the Earth so that the Earth doesn't get in the way of the view. And because the Earth is bright, and so that's sometimes the glare from the Earth ruins our images.
We have had some guests on our program who have talked about an extraplanet in our solar system. They call it Nibiru, and they say that it's on a 3,600-year elliptical orbit, since you brought up elliptical.
Yeah.
And that it, comes in close and then goes way out, and every time it gets close, it has some kind of havoc on our planet, Earth-wise conditions and stuff like that. But is it conceivable, Josh, that there is another planet like that in our solar system? We just haven't found it yet?
So it is conceivable that our solar system has another entire planet that we have not yet discovered. But like I said, planets are small, and they're generally very faint. So there could be a planet in the far reaches of the solar system that has not yet been detected.
If it were Jupiter-sized, would it be easier to find?
Yeah, if it were Jupiter-sized, I think we would have found it. But there is room for a planet, say, the size of the Earth, or even a few times more massive than the Earth, as long as you put it out at hundreds of times farther from the sun than we are. It would be faint enough and inconspicuous enough that we might have missed it. And in fact, that is a topic of a lot of current interest. Now, The theory that you described a moment ago about this planet that is on I think you said every 36,000 years it comes in.
3,600.
Yeah.
3,600.
Honestly, I have not seen any evidence for that kind of planet. But there is indirect evidence for a planet that is sometimes called Planet 9. It's called the Planet 9 hypothesis. And the evidence is interesting. We don't see the planet, not yet at least, but we do see something funny going on in the Kuiper Belt.
Interesting.
Remember a little while ago I said that
you mentioned that.
In addition to the asteroid belt, which is between Mars and Jupiter, there's this outer belt of debris and small bodies, rocks and chunks of ice called the Kuiper Belt. And so a lot of people, a lot of astronomers like to find objects in the Kuiper Belt and track their orbits as a way of learning about the early events that took place in the solar system.
Hold on for a second, Josh. We're at the top of the hour. We'll come back, and I want to talk about this Planet 9. We've heard it as also Planet X. And then we'll take calls with Joshua Winn. His book is called The Little Book of Exoplanets.